Everybody. Alright, we are, I think, kind of in the early-ish part of Chapter 20. I don't think Chapter 20 is a hugely long chapter, and there's quite a bit of redundancy, fortunately for you guys, with Chapter 19. So if you got Chapter 19 down, you know, there's still topics in Chapter 20 to learn, but a lot of it's kind of builds on Chapter 19. One of the things we were talking about last time was that Alkanol Halides, or you could more generally just say acid chlorides are the big ones. Because it could be bromides, whatever, but we're generally focusing on chlorides. And then alkanoil kind of means like an alkane, and it's more broadly just, you know, the acid chloride functional group. React with organometallics, and they do it. The reactivity is different if you use a Grignard, which is like a R-MGBr, or an organolithium. Those are, generally speaking, they do the same thing. So Grignards, which are R-MGBr, and organolithiums, which are R-Li, will usually do the same thing. But it can be one behavior with those, and there's another behavior with, what's the other metal? The other metal that we use for nucleophilic reactions. And that's copper, and those are called cuprates, right? Okay, so I'll review from last time. And what we saw from last time was that like an acid chloride would react with a Grignard, and it's kind of like a NAS style reaction. It's actually two steps. I'm summarizing those two steps here. Usually this would not be okay on a mechanism for you guys, but at the same time, this mechanism is so silly that it wouldn't be a question I'd even ask you. So this kind of abbreviation of the mechanism is okay. Attacks, electrons go up, and then you have an intermediate, and then electrons go down, and then kick off the chlorine, and so then you get a ketone, right? And then a ketone, of course, reacts with the Grignard again to make a tertiary alcohol like this. So that's kind of what happens with either a Grignard or an organolithium. But with a copper cuprate, like a phenyl to copper lithium, it, for whatever reason, stops at the ketone, and there's some subtlety in the mechanism of why it does that. I don't have an easy answer. I think the book talks about it, but it's not a big deal. To me, I'm just, you know, happy to know that just the outcome here. This is not an interesting mechanism, I don't think. But essentially, the phenyl 2 copper lithium attacks the same way. Electrons up, electrons down, kick off the chlorine. But a ketone just does not is not reactive with more cuprate. So the ketone is the final product when you react with a cuprate. Okay, so that's cool. It's like one behavior with Grignards and one behavior and organolithiums, and another behavior with cuprates, right? And analogously, in addition to addition of R- reagents, or, you know, like organometallic reagents, we call them R- because it's R and then a dot minus and it reacts. We can also do the same thing with H- reagents, right? H dot minus. What are H dot minus reagents called? H dot minus. What's that? What's the word you use to describe H dot minus? There's a word. It's not proton. It's not a radical. It's called hydride. So the concept of H dot minus is called a hydride, and there's a couple of hydride reagents that you know of, and we learned them in Organic 1, like NABH4 and LiAlH4. Those usually we learned react with ketones and aldehydes and reduce them to alcohols, right? That's what hydrides do. Well, just like we have differential behavior with R- reagents, like Grignards and cuprates, we also have some differential behavior with H- reagents, like hydrides. And so you can either get a full reduction or a partial reduction. And first we show the full reduction. Typical example, lithium aluminum hydride. And in terms of the mechanism, I often just abbreviate LiAlH4 as the concept of H dot dot minus. Since it's a little bit of a simplification, I add the quotes. So the quotes mean it's not exactly the same, but it's, you know, reactivity-wise, it's kind of like a free H dot dot minus. Sometimes I use a little like partial equal sign. It's like that. Lithium aluminum hydride is kind of the same concept as that. Anyway, it does the same thing. This is a strong reducing agent, so it attacks, electrons go up, electrons go down, kick off the chlorine, make an aldehyde, and of course it does it again, because aldehydes are super susceptible to reduction, right? Yeah. Anyway, just like with the R- reagents, we also have an alternative H- reagent that stops at the aldehyde. And I don't have a simple mechanism for that, how that happens, but I do know the reagent is LiHAl 3 tertbutyls with oxygens. We could call this lithium tri-tertbutoxy aluminum hydride, right? Lithium tri-tertbutoxy aluminum hydride. Lithium tri-tertbutoxy aluminum hydride. That's what it is, right? Lithium tri-tertbutoxy aluminum hydride. But the thing is that it does stop at the intermediate point. And that's great, because if you need an aldehyde, we can totally make it from an acid chloride. And of course, there's 1,000 things we can do with aldehydes, right? We can do Grignards, we can protect them with acetals and thioacetals, we can make imines, we can make enamines, all those kind of things. There's a million reactions we know of aldehydes. So it's great that we have control over a double reduction, so it's like reduce once, reduce a second time, or a single reduction to the aldehyde. Okay? Yeah. Let's see. Okay, cool. Alright, so we're still in this section 5, which is talking about these acid chloride reactions. And we're still in F, which is kind of talking about the partial reduction stuff. Partial reduction, right? So just as a summary of those 4 things, we can draw this very nicely in a little figure where I'll draw an acid chloride. And we'll show, there's kind of like 4 pathways we can take. Using these kind of R- and H- reagents. And one is we can do a Grignard, R-MgBr. Another is a cuprate, R2 copper lithium. Right? Another is lithium aluminum hydride, and like acid, or just say water or whatever, water acid, whatever. And the other one is, what's that weird one that we just learned? It's another aluminum one. It's lithium. Fortunately, you guys in the open note class don't have to memorize stuff. I usually would not make you memorize the reagent, but I'd you know, if you can kind of make an association, you know, maybe three tertbutoxys or something, I don't know. Remember, there's a negative charge in aluminum also, water. That you could kind of remember, oh yeah, this is the weird one that does a single reduction, right? Okay, so this makes a tertiary alcohol, this makes a ketone. Right? Tertiary alcohol. Running out of space here. There's a ketone for the cuprate. Lithium aluminum hydride makes a primary alcohol. because we added 2 H's, right? There's the 2 H's we added. And then this one does a single reduction, so H minus attacks, does it once, and you get an aldehyde. That's a pretty cool way to kind of show this, right? Yeah, and what we're going to see is some of it, like this whole concept of like R minus 2 R's, 1 R, 2 H's, or 1 H will apply to other functional groups, not just acid chlorides. Like esters will do something like this too. So just kind of be ready for that. And there's going to be slightly different reagents, so it's good to kind of summarize them. I have a really good summary sheet that I'll give you guys a little bit later for all of the different functional groups and then the different variations with adding 2 R's or 1 R, 2 H's or 1 H. Sometimes we abbreviate these concepts a little bit more, because like here we're adding R twice, right? Sometimes we call this, we say Grignard is a R minus 2 equiv reagent, equivalents. So it's like 2 R minuses, R minus 2 equivalents, right? EQ, UIV, or like 2 EQ, right? A Grignard is a R minus 2 equivalent reagent. What's a cuprate? A cuprate is an R minus 1 equivalent reagent, right? For acid chlorides. There is a 1 EQ is a nice abbreviation, right? R minus 1 EQ, right? Because we're adding 1 R group, right? Now lithium aluminum hydride, how many H's are being added? 2, right? So we could call this a H dot dot minus 1, or sorry, 2 EQ reagent, right? Because we added 2 H's. And then what would the lithium tributoxy aluminum hydride be? It would be an H minus, how many equivalents? How many H's got added? 1 equivalent. H dot dot minus 1 EQ. So sometimes I'll use that terminology also, just to remind you, of course, what we're adding. 2 equivalents, 1 equivalent, right? Yeah. And also, I'll just mention right now, like this reagent does not react with all the other carboxylic acid derivatives. It only reacts with acid chlorides. So you should make an association between, yeah, this reagent and this functional group makes aldehydes. Okay. Alright, and now, that was number 5, talking about acid chlorides for the most part. Number 6 is chemistry of carboxylic anhydrides. Carboxylic anhydrides, I mean, of course, we know those is just anhydrides, right? It's what functional group? What's the structure of an anhydride? It kind of looks like an ester, but on both sides almost. Like here's an anhydride, right? Not an ester. If it was that would be an ester, right? That would be an ester, an ethyl ester. But this is not an ester. It's an anhydride. This specific one is called acetic anhydride. I would make a bet, and I don't know the answer off the top of my head, that this is probably the most commonly produced anhydride in the planet. This is a very, very commonly used reagent. It's used to make aspirin and other chemicals. This is just a very common one. A couple others that are known. And what's the general reactivity? We'll review it. But just, you can kind of assume like one side of this is a leaving group, like, right? We could attack the left one, and then the right side is a leaving group. Kind of like the whole right side's a chloride. Like, imagine this being an acid chloride, right? electrophile, and then leaving group, right? Okay. A couple other ones that are commonly used. There's this cyclic anhydride called succinic anhydride. The idea is you can attack like the top carbonyl, and that breaks off the sort of the bottom part as a leaving group, but it's still attached to the molecule. We may see that again. And we also have, this is a 5-member ring, there's also a 6-member ring version. This is called glutaric anhydride. Glutaric. And it's also something like you could attack the top carbonyl and that would break off the whole bottom part. But that would be basically tethered as a carboxylic acid. So you'd have like carbon, 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 and carboxylic acid. So like an amine might attack this, and then you have a tethered carboxylic acid, right? Okay. I'll say that, you know, typically this is not something we would make. Typically not something we make. But it's something we, like in the laboratory, like if I'm, you know, in an organic chemistry lab, it's not something I'd make, but it's something I'd use. So these are things you'd usually purchase commercially or whatever. So some are commercially available and used all the time. Commercially. And like I said, acetic anhydride is probably the most prominent of these. So if you need to attach an acetate group to an amine or an oxygen, yeah, you just go get your bottle of acetic anhydride, right? Okay. That said, we can make them. They are makeable. It's just not something we typically would make. So let's review how to make them, because it is really easy to make them. Like I could take an acid chloride and react with a carboxylic acid, right? This time, let's use formic acid. So this is going to make a kind of a special anhydride where one side's a little different than the other. I think we mentioned this one before. I'll draw the product first, and we use a little bit of base. The base is probably pyridine or something. But it's essentially, it's going to be oxygens connected to carbon, right? That oxygen's connected to that carbon. So yeah, something like that maybe. Mechanism of this is very easy. It's a NAS reaction. Let's say nucleophilic acyl substitution. Yeah, but remember, usually the nucleophile just attacks and then the base takes off the proton. But if you have a highly acidic proton, this is like pKa 3 or 4, the base will just take off the proton first, and then the mechanism is incredibly easy. So in this case, base takes proton, a negative charge somewhere, or negative charge, okay, whatever. And then circle the lone pair, and then electrons go up. Electrons kick onto the acetyl bond O. Right, and then in a typical NAS style reaction, oxygen kicks in, kicks off the chloride, and then you make your product, right? Okay. Yeah. So, and then this is like, if you look at the other anhydrides we talked about, like acetic anhydride, succinic anhydride, and glutaric anhydride. These are all called like symmetric anhydrides because it's like the same things on both sides of the oxygen. This is not symmetric anhydride. This is, we often call these mixed anhydrides. Because you have one thing on one side, one thing on the other, okay? And imagine we're going to use this as a reagent, because this is kind of analogous to an acid chloride, right? You got a, you know, an electrophilic C double bond O, and then you have a leaving group. And which side is going to be attacked by an electrophile, sorry, nucleophile? Like if you're a nucleophile and you're going to attack, which side are you going to attack? Probably the sterically least hindered side, and that would usually be the side with the H on it, right? And so this is a great way to for a nucleophile to attach this group onto your, like, nitrogen or oxygen or whatever, and we'll show that in a second, okay? But this is called a mixed anhydride. Okay. Okay, so we're still on anhydrides. That was kind of how to make them. That's, you know, making them from an acid chloride is really easy. You can make any anhydride from an acid chloride and a carboxylic acid. The same thing I just showed you. There's other ways to make anhydrides too. And then the key use of anhydrides, using anhydrides, right, is to make amides or esters. That's usually what we do use an anhydride for. So is an example, I have an amine. I want to make a acetamide, which is a amide with acetate, essentially. How could I possibly do that? Of course, a million ways I could do that. You could use an acid chloride, right? You could use the acid chloride of that. But the anhydride is actually a maybe cooler than the acid chloride, like in terms of lab safety and stuff, because this is a little less toxic. It doesn't create HCl when you react with it. So this is kind of maybe a preferable method to using the acid chloride, which would be acetyl chloride. We could totally use this acid chloride to do this reaction. But then your byproduct's HCl, and HCl is a little toxic and nasty. The byproduct here is actually just acetic acid, which is a little less nasty. We usually need a base, and a pyridine would be your base of choice. Okay. I talked about the mixed anhydride, and I'll just show an example of that. So if we use the same substrate, how could we make a formamide, which is, this is an acetamide, this is a formamide. The best way to make a formamide is using the same kind of anhydride, but with an H on one side. That's that mixed anhydride idea. So again, here the nitrogen's deciding where am I going to react, left carbonyl or right carbonyl, and the right side one is less sterically hindered, so it's going to attack the right side one. Electrons go up, electrons go down, kick off the oxygen, and kick off the leaving group. Usually you react with pyridine as well. All right, so you can make amides this way. These are very common ones. This one's not commercially available, but you can make it really easily, like I just showed a couple seconds ago. Another key use is to make esters, right? You can make amides, you can make esters. One example is aspirin, the synthesis of aspirin, right? So this is salicylic acid, salicylic acid. And if you want to make aspirin, which is acetyl salicylic acid, you would react this with acetic anhydride. Usually with something like a base like pyridine as well. The more reactive oxygen is the phenolic oxygen on the bottom. This one's less reactive because it's resonance stabilized. But essentially the mechanism is oxygen attacks, electrons go up. At that point the pyridine would take off this proton, right? First this attacks, then the pyridine takes off that proton, and then oxygen swings down and kicks off the right side as a leaving group. But this is aspirin, and I'm pretty sure this is like the commercial synthesis of aspirin that they do on multi-ton scale every year. All right, cool. And the aspirin synthesis is actually, it's a really well-behaved reaction. Like, I taught a high school level organic chemistry class, lab class one time, just to expose students, high school students, to organic chemistry. And one of the things they did was this reaction, because you could do this in a test tube even. You just take a little bit of this, a little bit of that, cook it, and then pour it in water, and you get crystalline aspirin. And this is also our experiment 1, I think, of the Organic 2 lab, chem336. So just to get you kind of like introduced to doing reactions in the laboratory. So yeah, it's a very cool, doable organic reaction. I'm going to show just one more random example of using anhydrides to make esters in a more complicated molecule. This is a steroid. Steroids have this sort of 6-member ring, 6-member ring, 5-member ring type of structure. Methyl, benzene, OH. And we have a hydroxy group up here. This molecule is called estradiol. It's a female sex hormone, and it controls some of the sort of like growth characteristics in females. It's also, I think it has issues with, what was it? It's actually used as an estrogen supplement, I guess, in postmenopausal women. There's a lot of biological interest in this molecule. And, you know, as organic chemists, we just love reacting, you know, reagents like anhydrides with molecules that have alcohols in them. And this is an example of something we can react with acetic anhydride. A little bit of pyridine. We have 2 alcohols. They both get reacted to make acetate derivatives. So, acetate up there, and the acetate also on the aromatic alcohol. So this is like a estradiol diacetate, I'd probably call it. Estradiol diacetate. Okay, cool. All right, that's it for anhydrides. Not a ton of new stuff to know about anhydrides. Esters now, chemistry of esters. Well, esters are a little more prominent as a functional group. We use esters for a lot of things, a lot of reactivity related to esters. So maybe I'll put a star, like, to suggest esters are a little more important, I guess. Now the book, I think, jumps in and talks about all the conceptual details about esters right about now. Now I reorganized my lecture to put those conceptual details in the PowerPoint. So we already learned about the conceptual details and the naming and the structure of esters, so you can review that. And I'm just going to jump into the chemistry and first review, how do we make esters? Making esters. There are three essential methods, I guess. And this is mostly review. I think you know all of these methods. I'm just summarizing them again, the three methods. The first one would be using a more reactive carboxylic acid derivative. So, like an acid chloride, you can convert an acid chloride into anything of any of these carboxylic acid derivatives. You could either use an acid chloride. You could also use an anhydride, right? As we just saw 2 seconds ago. That's one way you can make esters. So as an example, if I have benzoyl chloride, which is a very boring acid chloride, and I react it with methanol, I need what kind of reagent to make this work? Some kind of base to absorb HCl. Typical base we can always use is pyridine. Super easy. We've done this many times, even through chapter 19 yet. This is base-mediated NAS. So the idea is oxygen attacks, then the base takes off the proton, then the oxygen kicks off chlorine. And we can kind of summarize that mini mechanism as up, down, off, even though there's a couple little steps to that, right? Okay, so that's one way to make esters. You can make almost any ester this way, from an appropriate acid chloride or anhydride, and reacting with an alcohol, right? Okay, so what's number two? Number two is the Fischer method, from Fischer Sterification. The Fischer Sterification reaction does not use something like an acid chloride or anhydride. It directly uses a carboxylic acid, which is actually a terrible derivative. It's not a horrible leaving group, right? It's a horrible leaving group. So why does this work? Because you're not using base, you're using acid as a catalyst to essentially make this into a good leaving group, right? So that's what Fischer Sterification is. It's an acid-catalyzed reaction, right? Acid-catalyzed esterification. It's an equilibrium, so it can go back and forth. You get water. How do you force the equilibrium one way or the other? Usually, to force it, I would use excess of either that or that, and that'll use Le Chatelier's principle to force it over. I'm not going to review this because I showed it already. It's acid-cat, NAS. You saw it already. It's a cool mechanism. The basic gist is that the carbonyl, the C double bond O, gets the proton, makes an RSCC. RSCCs love to be attacked. Then the alcohol attacks the RSCC, proton transfer, kick off a leaving group, and you're done. Right? That's basically how this Fischer Sterification works. It's a cool reaction, a cool mechanism. I'm not going to just keep showing things over and over. I think we learned it. I think I taught you it in chapter 19. I think it was in chapter 19, actually. Yeah. I always ask in office hours too, and I'll review mechanisms, old mechanisms. Okay, well, we have one more method that you have not seen, but we're talking about esters, so let's talk about other methods to make esters. By SN2, remember that scary reaction from organic 1? Nucleophile attacks carbon, kicks off leaving group, remember that? So here's a way you can make an ester from an SN2 reaction, and we're going to do the same exact one we just showed. We're going to make this compound also from a carboxylic acid, but using SN2 to like make this a good nucleophile, and then go attack something with a leaving group, right? Could we use this? Could we attack this? Like somehow could we use this as a nucleophile and attack this carbon and kick off OH to make that? That's definitely not what this mechanism is, right? This is protonate the carbonyl, oxygen attacks, etc. But could we use this as a nucleophile to kick this off as a leaving group? The answer is no, because that's not a good leaving group, right? OH is a terrible leaving group. It's one of the horrible, worst leaving groups there are in organic chemistry. There are cases where OH is a good leaving group, but not in an SN2 reaction. We did see it, I think, in like the Wolff-Kishner, where there's a couple cases where OH can be an okay leaving group, but not in an SN2 reaction. So if we want to make this product from this being a nucleophile and attacking something with a leaving group, what's the essential thing we have to do? We have to use a good leaving group. So what's a good leaving group? Do you know any good leaving groups? Remember good leaving groups from organic 1? So what we're going to do is first we're going to react with NaOH, just a base, take off the proton, make a good nucleophile. So what is a good leaving group that we could use instead of OH? Good answer is bromine. Bromine's a great leaving group. Okay? And what's the good solvent for SN2 reactions? What's the good solvent for SN2 reactions? Like DMF. Remember DMF, it's a polar aprotic solvent, great for SN2 reactions. Well, that beautifully makes an ester. It's the same ester as we just drew up there. Okay, and what's the mechanism? What does the base do to a carboxylic acid? Bases take protons. What's it called if you have a carboxylic acid minus the proton? It's a carboxylate. Right? Is this, which is a better nucleophile, a carboxylic acid or a carboxylate? Like, could I just skip step 1 and just use that as a nucleophile? Use the carboxylic acid as a nucleophile? Well, you possibly could, but if you remember from organic 1, what things are better nucleophiles? Neutral things or charged things with a negative charge on them? The answer is the charged with a negative charge, because you're going to go attack this carbon, right? And why does an SN2 reaction even work? Well, because this is delta minus and this is delta plus, right? See that? I'm going to draw it. So the carbon is delta plus and the bromine is delta minus, right? The bromine is pulling electrons towards itself. And that makes this carbon electrophilic, likes to be attacked. Delta plus. So who's the best thing to attack delta plus? A negative charge, right? So now this just swings in, attacks the carbon, kicks off the Br, and guess what you got? You get the product, right? So that's cool. It's an alternate way to make esters. Nothing wrong with this. This is actually a great way. We also have the Fischer method and the acid chloride / anhydride method. I should say between method 2 and 3, is there any is there any advantage to method 2 or method 3? Like, is the fact that this is an equilibrium, is that good or bad for method 2? It's kind of bad because it can go back and forth, right? Sometimes it's hard to go completely from left to right because everything's in equilibrium. And this is actually irreversible. It's like irreversible step, irreversible steps. So you might say, well, method 3 is actually probably the better method to do this. The only big downside to method 3 is these reagents, these alkyl halides, like the isobutyl bromide thing, are carcinogenic. So your DNA is nucleophilic. These things are electrophilic. So you could imagine, like, if you breathe this or get it on your hands or whatever, this could potentially cause cancer or something. And they are kind of mutagenic and sometimes carcinogenic. So you have to be really careful with alkyl halides. Whereas most carboxylic acids are non-toxic, most alcohols are non-toxic. So this, you're dealing with less toxic stuff. So that's definitely one difference between method 2 and method 3. All right. Okay, so we're still on number 7, esters. We're still on A, which is making, how to make esters. And we're still a little bit on number 3, which is this SN2 method. I just wanted to mention something from, actually going back to Organic 1, so scary Organic 1 stuff. Many chapters ago, I think it's around chapter 9, you learn about a way to make alcohol. I mean, it's 9 or 8, I forgot. I should know this, but I don't know the entire textbook in my memory. But you learned a way to, if you say you have a bromide like that, and you want to convert it to an alcohol. Now it will be inverted, but that's not really the point of what I'm talking about. We were learning about how to make alcohols, right? And sometimes you can just do an SN2, right? Like, right, you could just imagine hydroxide, OH minus attacks, kicks off the bromine and makes this, right? You could almost imagine this working. You're like, well, I want to go from a bromide to an alcohol. And that actually does work in certain situations, like if it's primary, but primary and like methyl, I guess. This actually has a problem though, because this, it looks perfect, right? But it doesn't work, and the reason it doesn't work is because it would rather do elimination. Remember that when you do SN2, this is an SN2 reaction, sometimes you have competing elimination, and especially if the substrate's kind of hindered, like a bromide, or I'm sorry, the secondary and tertiary alkyl halides often have competing E2 reactions. It's like you want to do SN2, but it doesn't do SN2, it does E2. Okay, because this is congested and whatnot. So we had a solution to this, and this is a little bit of a tangent, but it'll all make sense in a second. The solution was, you may remember this if you're really attentive in Organic 1, the solution was a two-step procedure using acetate and DMF, like sodium acetate, like Na plus and there's acetate, right? And that's a good nucleophile. And then like hydroxide. And back in Organic 1, I always say that you can learn, you'll know a little bit of this mechanism, but the rest you have to learn in Organic 2. And now we're in Organic 2, so we can talk about the mechanism, right? That's not connected. These are not, like DMF is a solvent, right? So DMF is a solvent. Acetate is just a nucleophile. And this is all connected to number 3 here, this SN2 reaction to make esters. Okay, so let's just think about step 1 real quick. What does step 1 do? Well, this is a very nice, well-behaved SN2 reaction to make an ester. To make an ester, like we're talking about, making esters by SN2 reactions, right? And it inverts the stereochemistry because SN2 reactions invert the stereochemistry. Very cool. And this, you understood this in Organic 1. This was like chapter 8 or 9. I think it was 8. Maybe it was 8. 8 was learning about alcohols and how to make alcohols and stuff. And so this was actually something we could understand in Organic 1. And now we see it again, making esters. This is, our topic number 3, SN2 reactions to make esters, right? But what I said in Organic 1 was this reaction is totally way beyond Organic 1. This is like not an Organic 1 reaction, right? Going from an ester to an alcohol was not Organic 1 knowledge. You did not have any idea how to do this because this is you're in chapter 8. This is chapter 20, right? So now we're like 12 chapters away. Now we know how to actually do the second step, right? How do you cleave an ester? That's a good question. You should know the answer to this because we have already talked about this even in last chapter, chapter 9. How do you hydrolyze an ester? Well, it's really easy. It's OH minus, right? Hydroxide. It's also called saponification. Saponification, right? And this is actually a 2-step process: hydroxide and then like acid water. But what this does is sorry, I screwed up. It does not attack there. It attacks the carbonyl of the ester, right? This is a NAS reaction itself. Electrons go up, essentially electrons go down, electrons go off. And that's how you cleave an ester to make an alcohol. But in Organic 1, this is all demonstrated as I can convert a bromide to an alcohol. And we'll just talk about this later in Organic 2. The byproduct is acetic acid, right? Okay, and we're going to review saponification in a second also, just in case you've forgotten about saponification. Okay, so this was a cool, thinking back from Organic 1, chapter, I'm pretty sure it's chapter 8 actually, of like how to go from a bromide to an alcohol, especially in a secondary carbon, and avoid this whole elimination business. Because this does not cause elimination. This is a very well-behaved reaction. All right. Okay, so we're still on the 7 esters. Now we're on B, which is we learned how to make esters by 3 methods: acid chloride, Fischer, and the SN2 reaction. Let's talk about the reactions of esters now, and the first one will be, just like I mentioned, hydrolysis of esters. So one thing you can do, kind of a boring reaction of esters, is hydrolyze them back to a carboxylic acid and alcohol. And the first method is saponification. And saponification is just base mediated. By base mediated, I mean OH minus, hydroxide, right? So, example. Got an ester. I want to hydrolyze it. Basically, I want to cleave the bond. I want to cleave that bond, right? Yeah, I want to cleave this little the C to O bond. And I'm pretty sure you saw this already. We'll do it again though. Again, there's a redundancy between this chapter and last chapter. So we usually use like methanol as a solvent. So it's NaOH, methanol, H3O. And you always have an acid step afterwards, and the net reaction is just cleavage of the CO bond, and you get a carboxylic acid, and then like methanol. Alright, so what is the bond we're cleaving? It's essentially this is the bond we're cleaving, right? That's the bond we're cleaving. Alright, so what's the mechanism of this? Remember, this is actually kind of cool that it's all reversible initially. So you have hydroxide as a nucleophile. So it attacks the carbon and kicks electrons up onto the oxygen. Now it just kicks off the leaving group. And this is still in equilibrium. And you might think, oh, equilibrium reactions are kind of bad because it can kind of go one way or the other, right? And that's usually the case. That's a problem, right? Because if you want this as your product, so you have these equilibrium steps, that's kind of a problem, right? So then we have O minus CH3. But this is a super strong base, and this is a super strong acid. So once this falls off, this methyl alkoxide, or methoxide, I guess you'd say, methoxide, or methyl alkoxide, those are both the same thing. This can rip off this proton, and that's actually irreversible. When you have a strong base and a strong acid, and the base takes the proton off the acid, that is, for the most part, an irreversible reaction, right? So that's why this all works, is you have like reversible, reversible, irreversible. And when you have a series of like reversible steps followed by an irreversible step, that'll force the whole equilibrium forward. So it gets to this point. Now this is a pretty happy molecule, that's a pretty happy molecule. So we went from, you know, reversible into the irreversible steps. And then once you got this, then you can do a second step of H3O plus, and that's also irreversible, depending on the acid strength. And net effect is it's essentially what we consider a irreversible reaction from starting material to these two products. Okay, that is base-mediated hydrolysis, or saponification. We also, another way to hydrolyze esters is the acid-catalyzed hydrolysis, which is I also call the reverse Fischer, because it's the Fischer in reverse. I'm not going to review that, I'll just draw, I'll set it up, you can do it. Okay, same one, methyl ester, and we can hydrolyze this using like water and catalytic acid to the carboxylic acid and methanol. Right? And I'm not going to review the whole mechanism, I'll just kind of get it started for you. It's all equilibrium, and you usually use excess of this, just use tons of water. And what happens, it will force the equilibrium from left to right because you're using excess water. The basic idea of the mechanism is protonate the ester and then make an RSCC, water attacks, proton transfer, kick off methanol, basically, etc. So that's, this is, I'll say, this. You could draw this out, and you can practice it now or look in your notes because we did it before. Okay, that's another hydrolysis method of esters. Solid esters. One thing you can do using NAS is convert esters to amides. Convert esters to amides, because remember when we started with all of these carboxylic acid derivatives, we went from the reactivity of the leftmost reactivity all the way to the rightmost, and we said acid chlorides are the most reactive, then anhydrides, then esters, then amides, then carboxylic acids. And we said it was really easy to go from left to right because you're going from a more reactive thing to a less reactive thing. Well, anyway, an ester is a more reactive thing and an amide is a less reactive thing. So it's really easy to go from an ester to an amide. That's what I'm trying to say here. So if we have an ester and we want to turn it into an amide, all we got to do, and it makes methanol as a byproduct, is heat a little bit. These things react, and this is a better leaving group. This is a better leaving group than this. So and this is also happens to be a base too. So we don't have to add a base like pyridine because we already have a good base. We have a good base and we have a good nucleophile. So it just attacks. Usually I think we just proton transfer from the nitrogen to the oxygen. Don't forget your charge on the nitrogen. So we PT. And then we just kick off the methanol. Very non-exciting mechanism. We have exciting mechanisms. This is not the most exciting mechanism. It's just another NAS, right? Base or nucleophile attacks. We usually to make this mechanism easy, we just proton transfer from nitrogen to oxygen, make oxygen a good leaving group. O- kicks off the leaving group, and then you're done. Right? Not too exciting. This reaction is also called, not hydrolysis, because we're not hydrolyzing it. It's sometimes called amidolysis, or aminolysis. Aminolysis of esters, right? Okay, not too exciting. Okay, still on esters. Next one. Remember when we did acid chlorides? How we first talked about the Grignards. We did the Grignards and cuprates and the different kinds of H- reagents, right? Well, that's what we're going to do now, but for esters, because we're still on esters. So reaction with organometallics. Alright, and this is a little easier than acid chlorides because we don't have like different behaviors. We only have one behavior. So the behavior is R minus adds twice. That's it. You don't have an option, it just adds twice. And by R minus I mean our Grignards and organolithiums. Alright. What's the other metal? We know about magnesium, we know about lithium. What's the third metal? Cuprates. Well, I'm happy to note for you that cuprates do not react with esters. NR. No reaction. So cuprates are not... Cuprates do react with acid chlorides, but they don't react with esters. Okay, so let's just show a reaction with an ester now, methyl ester, for example. And let's show how it reacts twice with, like, phenyl magnesium bromide. MgBr. And maybe a little bit of acid. Okay, so what's going to happen is that's of course a good nucleophile, right? And I'm just going to do our I'm going to do our miniature NAS mechanism, right? A miniature NAS mechanism, which is it attacks, electrons go up, and then electrons go down, and electrons kick off the leaving group. So that's, you know, we're abbreviating a bit. It's really two steps. It's like, first step, it attacks, and electrons go up. Second step, electrons go down and kick off the leaving group. But that's all I really care to show, because it's not that exciting, and we're trying to save time for the more exciting stuff. And you get a single addition to a ketone. And I could just write NAS, and we should understand what that means. NAS means it's not a single-step mechanism, it's a two-step mechanism, or two or more. But Grignard attacks, electrons go up, electrons go down, kick off the leaving group. But, just as we always know, ketones don't stop. Ketones see Grignard, they keep going, right? So this is not the final product. Ketones love Grignards too. Love to react with Grignards too, right? So we have more Grignard, and now the Grignard attacks again, electrons go up, and then at the very, very end we have that water step, which will give us a tertiary alcohol. My bad, that's not a phenyl over here. It's 3 carbons. 1, 2, 3. Okay, cool. So that's what esters do when they see Grignards. Grignards add twice. First it makes a ketone transiently, and then Grignard attacks again, and then, you know, we're assuming that water step is the very last step, H2O or acid or whatever, which will give us the proton on oxygen. Okay. I think the book mechanism may go into more detail. And that's okay. We're not that interested in this reaction because it's we need to know the basic idea of the reaction, but the mechanism is not that exciting. So our mechanism is sufficient, I'll say, for at least for our class. Ours is sufficient for chem335. Okay. One more example of this. What if we have this ester? It's a cyclic ester. Ooh, scary. And we are cyclic. This is a cyclic ester, right? Just as a little terminology note, Cyclic esters are also called lactones. So if you ever hear of a lactone is a cyclic ester, a lactone. Okay? Let's pick a Grignard to attack this molecule. I don't know, what's your favorite Grignard? Favorite Grignard? I don't know. Ethyl Grignard, which is ETMGBr. Remember, you can also use lithiums for the same purpose. I'll draw the product, you can figure out the mechanism. So, of course, the product is going to be that, this is going to get cleaved open. This is going to get cleaved open at that position. And then we're going to have two ethyls, right, on that carbon and a tertiary alcohol. So, I'll draw the product, you can figure out the mechanism. Ethyl. Let's see, we have carbon, 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 OH. Ethyl 1, ethyl 2. Right? You can try the mechanism. I'll show the first step. Ethyl, just you circle the bond because the bond is nucleophilic. Attacks, and then the electrons go up. Then you can draw that intermediate. It'll be ethyl attached, O minus, and then the O minus swings down and breaks this bond and kicks this open, and you get a O minus, right? You'll have this. This will be an O minus temporarily, and that will be an O minus also. There'll be both O minuses, and then. Well, actually, no, I'm sorry. The nucleophile attacks, you get an O minus, right? And then the O minus swings down and makes a ketone, and then this becomes an O minus, right? And then you got a ketone, and the ketone gets attacked again, and so you should be able to draw this. I can step through it in office hours if you want help with it. That's a fun mechanism. It's pretty simple. A pretty simple mechanism. All right. Okay, still on esters. And we did our explanation of organometallic reactions with organometallics, and only Grignards and organolithiums, but no cuprates. But now we're going to do E, which is reactions with reducing agents. And by reducing agents, we mean H minus reagents, right? H dot dot minus. And remember, there's kind of two ways you can imagine addition of two H minuses, or I can imagine addition of one H minus. So I can imagine H minus 2 EQ or H dot dot minus 1 EQ. And the same applies to like a Grignard or something. That was the last section, D. But for Grignards, there was only R minus 2 equivalents, which was Grignards. There wasn't an R minus 1 equivalent reaction. All right. Okay, so I'll show both of these. The first one, I'll do like an ester. And the two H minus 2 equivalents is simply lithium aluminum hydride. It's the super reactive H minus reagent, and this is essentially H minus 2 equivalents, meaning we're going to add H twice. Okay. We will also see an H minus 1 equivalent reagent in a second. All right. And a little bit of acid or water. Okay, and the mechanism is totally easy. So this stuff is essentially H dot dot minus, in quotes, hydride, right? And it's going to react in a NAS style reaction. Electrons go up, electrons go down, kick off the leaving group. Alright. NAS, right? That's what NAS is. And what is the thing we make there? H minus attacks. Ethoxy goes away. What do you get? Aldehyde. Okay? Which is very, very electrophilic and reactive, and like always, this is super reactive. It's going to react again. So lithium aluminum hydride reacts again. H minus reacts again, right? And of course, this is all organic one. It attacks, electrons go up, and then we have our water step. Is later in the mechanism because it's step 2. This is all like step 1, and then this is like kind of that step 2 with the acid water, and the final product should be a primary alcohol, right? Nothing too crazy, right? Nothing too crazy about that. Okay, so then what is the H minus 1 equivalent reagent for partial reduction? You should actually have a pretty good guess, because we saw a partial reduction of acid chlorides, right? It was that weird HAl triterbutoxy. Is lithium triterbutoxy aluminum hydride. And just to make things fun, that's not what we use for esters. Esters uses a different reagent. So it's a partial reduction using a different reagent, specialized reagent. So not everything's simple in organic chemistry, but this is open notes, so you always have your notes, and no big deal, right? To do a partial reduction, and by partial reduction I mean H minus 1 equivalent. This is obviously H minus 2 equivalents because you added one H and you added a second H. So for esters, we'll use the same substrate. So we use something called Dyeball. I'll draw the structure of it. Dyeball H. H3O plus. It's also called, sometimes it's also called, depending on the textbook, sometimes people call it Dyeball. AH, Dyeball H or Dyeball H. Those are the general names that are used. And it gives you an aldehyde. It's an H minus 1 equivalent source. Okay? Alright, so let me draw the structure of Dyeball, and I'll show how it does this. This one, there's actually a pretty nice mechanism. So Dyeball is this stuff. It's aluminum. It's that. It's diisobutyl. Those are isobutyl groups. Remember that from Organic 1? Isobutyl. It says diisobutyl. Isobutyl aluminum hydride. It's just a different hydride source. And it's Dyeball. Yeah. Okay. And the abbreviations are either Dyeball or Dyeball H, sometimes used, or Dyeball. All three of those are understood. Okay. All right. So it's a hydride source. It's just another weird hydride source. So it's essentially a different one that has different reactivity. So it's H dot minus. And what is it going to do? It's nucleophilic. It's electrophilic. Nothing crazy. Nothing crazy. It just attacks, right? Okay, so what does that give us? Here I'm going to step through it because it's actually kind of a cool mechanism. So it attacks and and electrons just go up, and you get phenyl O minus. You got your H, and you got your ethoxy, and this now has the aluminum still has its isobutyl groups, and this is plus charged, and this is all here. Now normally what would happen at this point, you got your O minus, you got a leaving group, and the O minus might swing down and kick off the leaving group, right? Make the aldehyde, and then it get reduced again potentially because aldehydes are so reactive, right? Alright, so that's usually what happens. But there's something special about this one. This is temporarily stabilized. Temporarily stabilized. What are these intermediates called? Where it's like a tetrahedral center and it's sp3. The intermediate of a NAS reaction, it's a tetrahedral intermediate. Right? We used that word before. Tetrahedral intermediate. It's a temporarily stabilized tetrahedral intermediate. So it does not collapse like normal. It does not collapse. By collapse I mean O minus, swing down, kick off ethyl, make the product. So it's temporarily stabilized until you drip in your H3O plus. So the H3O plus is that second step, right? The acid. And this H3O plus destroys any excess hydride. Destroy Dyeball. So no more reducing agent. It destroys the reducing agent, and it also converts. What does it do to the O minus? What's O minus going to do when it sees H plus, essentially, right? O minus gets the proton. Cool. Now this thing falls apart and makes the aldehyde. Lose a proton and you're done. So Dyeball is a pretty cool reagent in terms of we can sort of step through and understand each of the, how it works. Why does it only give a single reduction and not a double reduction? It's because it makes this stabilized tetrahedral intermediate. Okay? And when you add the acid, the H3O step, that creates an intermediate that does fall apart, but it also destroys the reducing agent, so there's no more reducing reagent around that would potentially reduce the aldehyde. And that's why lithium aluminum hydride, it doesn't do all that. It just reduction. It gives a double reduction, whereas Dyeball does only the single reduction. Okay, anyway, went a little bit over, and sorry about that. I just wanted to get through this concept of Dyeball, and we are done. We're actually making some pretty good progress. All right, see you guys.